Hi children, I am again back with the solid state. In the last session we have seen characteristics of solids, classification of solids based on the arrangement of particles, and classification of solids based on the binding force between the particles. In today's session we will make an in-depth study about the crystal structure. To begin with, crystalline substances consist of lots of crystal lattice. If we take one crystal, we can define it in this way as crystalline solids have definite and ordered arrangement of particles, or we can say crystals consist of atoms or ions which are arranged in a definite and ordered fashion. And this leads to a three-dimensional crystal structure. So a crystal lattice is defined as a definite and ordered arrangement of particles in a three-dimensional way. Again, crystal lattice is defined as a definite and ordered arrangement of particles. The particles may be atoms or ions in a three-dimensional manner. When I say three-dimensional manner, I want to tell you one thing. We can represent a substance in three different ways. First one is one-dimensional way. In one-dimensional way, we need only one parameter, that is the length. This is one-dimensional way of representing a substance. Another type of representation is two-dimensional way. For representing a two-dimensional way, we need three parameters. One is the length, another one is the breadth, and the third one is the angle between length and breadth. So in order to represent a three-dimensional picture or a two-dimensional picture or a two-dimensional substance, we need three parameters. They are length, breadth, and the angle between length and breadth. In order to represent a three-dimensional object, we need 6 parameters. The 6 parameters are the length, the breadth, the width or height, and the angle between length and breadth, angle between breadth and width, and the angle between length and width. Now, we are talking about crystalline substances. I told you crystalline substances consists of crystal lattice, and a crystal lattice, its definition I told you, it is the definite and ordered arrangement of particles in a three-dimensional way. Now, we will study more about crystal lattice. A crystal lattice consists of lots of simplest or basic units. I told you in crystalline substances, the particles are arranged in a definite pattern. When we arrange it in a definite fashion, we can take as basic unit, which is the simplest unit of the crystal lattice. I will show you this is a crystal lattice, and the unit cell I will show you. The full diagram is a crystal lattice, and which is a shaded one in blue color is the unit cell. A unit cell is the smallest portion of a crystal lattice. When repeated in different directions, leads to crystal lattice. So the basic unit of a crystal lattice is unit cell. So unit cell is represented here as a shaded manner, or a unit cell. I will show you here. This is a unit cell. And the particles, which will be either atoms or ions, are represented as spheres. And the position where the particles exist, we name it as lattice points. So these all are lattice points. This is the simplest unit of a crystal lattice, which is called unit cell, and this unit cell is represented in a crystal lattice. Now, we are talking about unit cells. Unit cells are of two types. They are primitive unit cells and centered unit cells. Unit cells are of two types: primitive unit cell and centered unit cell. In primitive unit cells, the particles or atoms or ions are seen only at the corner of the unit cell. Here the unit cell has the shape of a cube and the particles are seen only on the corners, only at the corners of the unit cell. Such types of unit cell are called primitive unit cells. Primitive unit cell, it is represented here. Lattice points are present only at the corner position of the unit cell. So this is a primitive or simple unit cell. Primitive unit cell is otherwise called simple unit cell. And centered unit cells contains particles at the corner positions as well as other positions too. So in centered unit cell, particles are present at the corner positions as well as on other positions too. Again, centered unit cells are classified into four, or centered unit cells are of four types. They are body-centered unit cell, face-centered unit cell, end-centered unit cell, and edge-centered unit cell. The first one is body-centered unit cell. In these types of unit cells, particles are present at the corners. This is a cube, so a cube is having 8 corners. Particles are present at 8 corners of a cube, plus one particle is seen at the center of the unit cell, or we name it as body-centered unit cell. So in body-centered unit cell, particles are present at the 8 corners plus one particle is seen at the center. Next is face-centered unit cell. In face-centered unit cell, particles are seen at the 8 corners plus particles are seen at the center of each face. We know for a cube there are 6 faces, one at the top, one at the bottom, and 4 faces are there on the plane through which we see. So a face-centered unit cell has 6 faces, and the particles are present at all the 8 corners plus center of each face. Here unit cell is seen, here another one, then here one, at the bottom one, at the back face one. The third category of unit cell is end-centered unit cell. End-centered unit cell mean particles are present at the 8 corners of the unit cell plus particles are seen at the center of any 2 opposite faces. Particles are seen at the center of any 2 opposite faces. Here we can see this is an end-centered unit cell. Here the corner positions are occupied with particles plus, and one particle is seen at the center of this face and its opposite faces at the bottom, and one particle is seen there. The fourth type of unit cell is edge-centered unit cell. Edge-centered unit cell contains each particle at 8 positions plus particles are seen at the center of the edges. A cube has 12 edges. So here we can see this is a edge-centered unit cell. The particles are seen at the 8 corners plus each particle is seen at the center of the edge. While talking about crystal lattice and about its basic unit called unit cell, it is unfair if I keep mum about 2 scientists, 2 British physicists, the father and the son. Their names are William Henry Bragg, the father, and William Lawrence Bragg, the son. And these father and son duo, they shared Nobel Prize in Physics in the year 1915. So far, this William Henry Bragg and William Lawrence Bragg are the only father and the son who shared Nobel Prize in Physics. And it is for the findings about the crystal structure. They did experiments with X-rays to find the structure of crystals. And they came up with a famous Bragg equation, and for this equation they received the Nobel Prize in Physics. And the equation is n lambda equal to 2d sine theta. And when we, dear children, when we meet each other in the class, I will discuss much on this topic as this is not there in the syllabus. So my children, now move on to number of atoms in a unit cell. So we studied about crystal lattice, we studied about unit cell and the types of unit cell. Now in each unit cell, how many atoms will be there? That is a way, that is a principle that we will see now. It is said in primitive unit cells, I told you there are particles at the 8 corners, and the corner atom, it shares with other 8 unit cells. Or we can say the contribution of a particle at the corner is 1/8 only to a particular unit cell. Again, may I repeat? The contribution of a particle or an atom at the corner position of a unit cell is 1/8 only. And in primitive unit cells or in simple unit cells, particles are seen at the 8 corners. So the contribution is 1/8 to the unit cell, or we can see total number of atoms in primitive unit cell or simple cubic unit cell is 1/8 into 8, which is equal to 1 atom. Or net, we can say in a primitive unit cell there is only 1 atom. At the corner position, we feel that there are 8 atoms, but the contribution of that corner atom is only 1/8 to a particular unit cell. In face-centered unit cells, I want to tell you one thing. An atom at the center of a face, it shares with 2 unit cells. So in face-centered unit cell, particles are seen at the 8 corners, plus each particle is seen at the center of the face. And you know, a particle at the corner, the contribution is 1/8 into 8, which is equal to 1. And there are 6 phases in a face-centered unit cell. So, and the contribution of each particle is 1/2. So, total number of atoms in face-centered unit cell is 1/8 into 8 plus 1/2 into 6, which is equal to 1 plus 3 equal to 4 atoms. In end-centered unit cell, particles are seen at all the 8 corners, plus particles are seen at the center of any 2 faces, which is in the opposite position. So, in end-centered unit cells, the total number of atoms is at the corner atom 1/8 into 8 plus the face center atom 1/2 into only 2 faces, so that is into 2, which is equal to 2 atoms. In edge-centered unit cells, particles are seen at all the 8 corners plus at the center of the edges. There are 12 edges, and I told you a particle at the center of the edge, it shares with 4 other unit cells. A particle at the center shares with 4 other unit cells. So the total number of atoms in edge-centered unit cell is 1 by 8 into 8 plus 1 by 4. Why 1 by 4 comes? Because a particle at the edge center shares with 4 unit cells. So the contribution of each particle at the edge is 1 by 4. So 1 by 4 into 12 edges, which is equal to 4 atoms. Thus, in a body-centered unit cell, the total number of atoms is 1 plus 1, 2. In face-centered, total number of atoms is 4. In end-centered, total number of atoms is 2. And in edge-centered unit cell, total number of atoms is 4. Now we know a crystal consists of unit cells, and we have seen several types of unit cells. Now, in order to represent a crystal, we need in 6 parameters to represent it in a 3-dimensional way. They are length, breadth, width, and the angle between them. So it is written here, a unit cell is characterized by its dimensions along the 3 edges A, B, C. A, B, C represents length, breadth, and width respectively, which may or may not be mutually perpendicular. It is not necessary that the edge lengths should be perpendicular to each other. Besides, we need the angles between the edges, which includes alpha. Alpha is between B and C, beta between A and C, and gamma between A and B. It is represented well here. This is an example for an unit cell and its dimensions. In order to describe a unit cell well, we need the dimensions A. This length is B. This is the length A, breadth B, height or the width it is C, and the angle between A and B is gamma, and the angle between B and C it is alpha, and the angle between A and C it is beta. These are the parameters of a unit cell. Based on this, scientists classified the substances into 7 crystal systems. So based on the different dimensions, scientists classified the substances into 7 crystal systems. They are, the first one is cubic. In cubic unit cell, the dimensions or the edge lengths A equal to B equal to C. That means the length will be equal to breadth will be equal to height, and the angle between all these is 90 degrees. Such types of crystals are called cubic crystals. So it is very easy. This is the most symmetrical crystal system. It is none other than cubic. Here the dimensions or the edge lengths are all same. A equal to B equal to C, and alpha is equal to beta is equal to gamma 90 degree. That means the edge lengths are perpendicular to each other. Another one is tetragonal. Tetragonal, A equal to B, but these A and B are not equal to C. So it is shown. Here always don't think, here this is a perfect cube, but here A will be equal to B, but C will be different. C is different. This is not a perfect cube. It is elongated one. So in tetragonal, A equal to B and these are not equal to C, but the angles alpha, beta and gamma are 90 degree. Another one is orthorhombic. Orthorhombic is A not equal to B, not equal to C. All the edge lengths, all the 3 edge lengths are different, but the angle between them is 90 degree. Alpha equal to beta equal to gamma, 90 degree. Another one is hexagonal. In hexagonal, A equal to B, but these are not equal to C, and alpha equal to beta 90 degree, but gamma it is 120 degree. All these are represented here. Next is rhombohedral. Rhombohedral, it is A equal to B equal to C, but the angles differ. Alpha equal to beta equal to gamma, but they are not mutually perpendicular to each other. That means they are not 90 degree, they are slightly slanting. Beside this, two more are there, monoclinic and triclinic. In monoclinic, A not equal to B not equal to C, but the angles alpha equal to gamma, which is equal to 90 degree, but beta is not equal to 90 degree. And triclinic. Triclinic, I will tell the feature. A not equal to B not equal to C, and alpha not equal to beta and not equal to gamma, and which is not equal to 90 degree. So I think, dear children, you will not forget about cubic system, cubic crystal system, and triclinic crystal system. Cubic crystal system is the most symmetrical, and triclinic crystal system is the most unsymmetrical crystal. So based on the variation in the edge lengths and angles, we have seen 7 crystal systems. But one thing, in all these 7 crystal systems, the unit cell is primitive. Unit cell is primitive, that means particles are present only at the corners. Now, in 19th century, another French physicist, his name is Auguste Brevet. He was not satisfied with the classification of crystals as 7 crystal systems. He did much studies, and it is said he locked himself in a room for 1 year with only basic things needed, and came out with his new findings. He said, it is not mandatory that crystals must be made up of primitive unit cells. It can contain centered unit cells too. And he came up with 14 types of crystal lattice, and he named it as Brevet lattice, after his name, Brevet lattice. Now we will see the 14 Brevet lattice. He said the cubic crystal system, it can be made up of primitive unit cell, body-centered unit cell, or face-centered unit cell. Though the feature is A equal to B equal to C and alpha equal to beta equal to gamma 90 degree, but it can be a body-centered unit cell or a face-centered unit cell. So, cubic crystal systems consist of 3 other crystal systems or crystal lattice. Similarly, tetragonal. Tetragonal can be primitive and body-centered. Again, orthorhombic, all the 4 types of unit cells it can be made up of. Primitive, body-centered, face-centered, and end-centered. And hexagonal. Hexagonal consists of only primitive. Rhombohedral consists of only primitive. Monoclinic. Monoclinic consists of primitive and end-centered, and triclinic also consists of only primitive. So based on that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So Brevet, Auguste Brevet came up with 14 types of crystal lattice, which is called Brevet lattices. Now, we have seen crystal lattice, we have seen what is unit cell, what are the different types of unit cell. Again, based on that, based on the primitive unit cells only, crystals can be classified as 7 crystal systems, and considering the centered unit cells too, crystal lattices are of 14 types called Brevet lattices. Now we move on to the three-dimensional close-packed structures. We know real substances exist in three-dimensionally. In order to make a three-dimensional object, we have to move through three stages. First, we have to make a one-dimensional close packing. We have to do one-dimensional close packing, then convert it into two-dimensional close packing, then three-dimensional close packing. In one-dimensional close packing, there is only one way. I told you previously, arrange them in a row touching each other. In one-dimensional close packing, arrange the particles in a row which touches each other. In between, I want to tell you one more thing. I want to introduce towards you a term, coordination number. Coordination number means the number of nearest neighbors of a particle. Consider this pink particle. It is in contact with two particles on its left side and right side. Here we can say the coordination number of this pink colored particle is 2. So coordination number means number of immediate neighbors of a particle. Coordination number can also be termed as coordinate number, or another term for representing coordination number is ligancy, L-I-G-A-N-C-Y, ligancy. So coordination number, this term is quite familiar to you, coordination number. Another term is coordinate number, or it is also called ligancy. Ligancy is a term which represents coordination number, and coordination number is the number of immediate neighbors of a particle. So you know how to make a one-dimensional structure. Now a two-dimensional close packing structure. What is to be done is take a one-dimensional structure and place the same above the first layer. The second row of particles, a two-dimensional close packed structure can be made by placing the one-dimensional row one over the other. This is a one-dimensional row and placing the same layer above it. Thus we can make two-dimensional close packed structure. So while talking about two-dimensional close packed structure, we can prepare it in two ways. Either above the first layer, which is represented as A, above the first layer, the second layer is kept exactly above the first layer. So if I represent the first layer with A, second layer also can be represented as A, because the second layer is exactly above the first layer. And such type of two-dimensional structures are called square close packing structure. Why is it called square close packing structure? If I take any particle, now the particles which is in close contact with it is 4, and if I join the centers of the immediate neighbors, I will get a square. It is represented with a red mark. So this type of arrangement is called AAA type packing or square close packing. So two-dimensional close packed structures are of two types. In one type, to a first layer, the second layer we are keeping exactly above the first layer so that both are vertically aligned. In such a case, the coordination number of each particle is 4 because it is in immediate contact with 4 neighbors, and when we join the centers of these neighbors, we are getting a square, and this type of packing is called AAA type packing or square close packing. Another way of representing a two-dimensional close packed structure is over the first layer, take a one-dimensional layer and over the first layer, keep the second layer in its depressions. It is shown here. The first layer is represented here, and the second layer, we are keeping the second layer over the depressions of the first layer. In the square close packing, we have just kept above it. We did not give importance to the depressions. But in the second type, we are keeping the second layer over the depressions of the first layer. This will lead to another type of two-dimensional close packing, which is called hexagonal close packing. Or if I represent the first layer with the letter A and the second layer with B, then the third layer will be exactly above A. The third layer will be exactly above A. Look, it is vertically aligned. And this pattern is called AB type pattern or hexagonal close packing structure. Hexagonal close pack structure. So you understood the two-dimensional close pack structures. In one dimension, we need to arrange the particles in a single row. In two-dimensional, we are keeping another row over the first layer. It can be done in two ways. Either keep the second row exactly above the first row, or keep the second row in the depressions of the first row, which give rise to two types of two-dimensional arrangement. The first type is called square close packing, and the second type is called hexagonal close packing. On to three-dimensional close pack structures. Almost all the substances around us we see are in three dimension. In order to make a three-dimensional close pack structure, what is to be done is, to a two-dimensional close pack structure, keep one more layer above it. Or we can keep many layers above a two-dimensional close pack structure. It can be done in different ways. The first method, you know, the same thing we have done in two-dimensional. In order to make a two-dimensional structure, take a single layer of two-dimension, and take another layer and keep exactly above the first layer. Then the pattern is same like square close packing, but square close packing we use the term only for two-dimensional structure. When it comes to three-dimensional structure, we name it as simple cubic lattice or AAA type lattice. I will show you here. This is a simple cubic lattice. This is the first layer. This is a square close packing layer. That means each particle is vertically aligned or horizontally aligned with each other. Now we are keeping a second layer exactly above the first layer. Then all the layers look same. This is a three-dimensional. All the layers look same. And so if I represent the first layer as A, second layer also will be A, third layer also will be A, or we name it as AAA type pattern or simple cubic lattice. Now, here the coordination number. If we consider one particle, 6 other particles are in close contact with it, and in simple cubic lattice, the coordination number is 6. Another way of making a three-dimensional structure is from two-dimensional hexagonal close packing. So for this, take a single layer, take a first layer. Now the second layer is to be kept on the depressions of the first layer. Second layer is to be kept on the depressions of the first layer. So when I talk about the depression, I want to tell you one thing. I want to bring to your notice one term, voids. V-O-I-D-S, voids or interstitial sites. These voids or interstitial sites are the depressions found between the particles when they are closely packed. Now these empty spaces or voids or depressions are of two types when we talk about three-dimensional structure. When I keep a second layer above the first layer. When I keep a second layer above the first layer, then the second layer I am keeping on the depressions of the first layer. That doesn't mean that all the depressions can be covered or all the empty spaces can be covered. It is shown here. It is shown here. The depressions that are covered is represented as T. And after placing the second layer, certain depressions are not covered. Such empty spaces are represented by O. They are none other than T stands for tetrahedral voids and O stands for octahedral voids. So once again I want to tell you, so in order to, while making a three-dimensional structure, first keep a two-dimensional structure on the ground or on the base. Over it, keep a second layer and make sure that you are keeping the second layer on the depressions of the first layer. Then a few empty spaces will be covered. That empty space which is covered is called tetrahedral void, and those spaces which are not covered is called octahedral void. Now, when we want to make a three-dimensional structure by hexagonal close packing, there are two ways. So the first way is arrange the two-dimensional layer. The second step is keep the second layer on the depressions of the first layer. So of course it will be two different layers and it is represented as A, this is B. First layer, and on the depressions of the first layer a second layer is kept, it is represented as B. It is represented as B. Now if I keep a third layer, there are two possibilities. I can keep the third layer on the tetrahedral voids, then I will get a pattern. I can keep the third layer on the octahedral voids, not the tetrahedral void, on the octahedral void, then I will get another pattern. So when the third layer covers the tetrahedral void, then the structure formed is of, if I keep the third layer on the tetrahedral void, the third layer is vertically aligns with the first layer. Vertically aligned, the third layer vertically gets aligned with the first layer. Then this type of pattern can be represented as AB, AB, AB type pattern, or another name is hexagonal close packed structure. Hexagonal close packed structure. So when I keep, again I will tell you, when we try to prepare a three-dimensional structure, keep a two-dimensional layer on the first as the first layer, then keep a second layer on the depressions of the first layer, then two types of voids will be formed, tetrahedral voids and octahedral voids. Then the third layer keep on the tetrahedral voids because they are depressions, tetrahedral voids. Then the third layer will vertically align with the first layer, and such type of three-dimensional close packed structure is called hexagonal close packed structure, or it's abbreviated as HCP. If the third layer I keep on the octahedral void, then that is shown here. If I am keeping it on the octahedral void, then the third layer does not align with the first layer. We can try this at home using oranges. Buy about 3 or 4 kilograms of oranges and we can try this. Then it will be very clear to you. If we keep the third layer on the octahedral void, then the third layer is not vertically getting aligned with the first layer. Then keep the fourth layer in the depressions. Then the fourth layer gets vertically aligned with the first layer. This type of arrangement is called cubic close packed structure. It is shown here, cubic close packed structure, or another name is there, face-centered cubic structure. Face-centered cubic structure. They are having the accepted abbreviations CCP or FCC. So CCP or FCC is one and the same. Thus, we prepared 3 types of three-dimensional closed packed structure. The first type is AAA type structure, or otherwise it is called simple cubic closed packed structure. Second category, the third layer covers the tetrahedral void. It is a hexagonal closed packed structure or XII. And the third type, where the third layer covers the octahedral void, then we are getting the pattern ABC type pattern, or cubic closed packed structure, or face-centered cubic structure. And from the examination point of view, usually the question comes, HCP type of HCP closed packed structure or hexagonal closed packed structure is seen in which all elements? The answer is, in the textbook it is there, in the syllabus it is there, it is magnesium and zinc. And CCP structure or cubic closed packed structure or FCC structure is present in non-reactive elements like copper, silver, gold. And in Cu, Ag and Au, this type of arrangement is seen. And now I want to tell you, in HCP and CCP, the coordination number is none other than 12, because both are effective way of arranging the unit cells or atoms. And how it becomes 12 as the coordination number? In the same plane, it is in contact with 6 members, above the plane 3, below the plane 3. So in both HCP and CCP, the coordination number is 12. Now from the examination point of view, another important thing, the relation between tetrahedral void and octahedral void. If a crystal contains n number of atoms, if we know the number of atoms, we can predict the number of tetrahedral voids and octahedral void. If an atom has n atoms, if a crystal has n atoms, then the number of tetrahedral void is 2n, and the number of octahedral void is n itself. So number of octahedral void and the number of atoms in a crystal will be one and the same. If a crystal has 20 atoms, then the number of octahedral void is 20 and the number of tetrahedral void is 40.